With increasing human-robot interaction applications, priorities have changed drastically. Unlike strong, fast, and precise rigid robots which work in predictable environment, safer and adaptable robots are needed. At that point, highly deformable and compliant soft robots attracted interests. Their inherently safe nature meets the requirements of adapting unstructured environments easily. On the other hand, their inherent softness brings along insufficient force and stiffness outputs which are crucial for manipulation and less precise motion. These challenges should be addressed to improve their functional performance and widen their application. To address stiffness control of soft robots, various techniques have been applied, from shape memory materials to fluidic-based solutions, like in our study. These methods can be used to control the stiffness of the whole body or just a part of body based on joints. Joint-based structures can be used to provide partial stiffness or bending shape control through proper stiffening actuation sequences. Among recent joint-based solutions, actuation and stiffness control have been obtained from different phenomena. For example, pressure-controlled stiffness of tendon-driven manipulator. We aim to reduce the control complexity and proposed a manipulator with independent pressure-controlled actuation and pressure-controlled stiffness. The proposed manipulator consists of two fiber-reinforced actuators, one stiffness control structure, and one encapsulation layer. We demonstrated independent stiffness and positioning capability of a 100 mm in length manipulator. Our manipulator includes symmetrically placed two identical soft actuators for bidirectional planar positioning. Each silicone rubber-based actuator was designed in semicircular geometry to reduce the bending resistance and reinforced with inextensible fiber to support elongation while limiting radial expansion. Upon pressurization up to 1.5 bar, each actuator deforms and generates pressure-dependent stiffness. The second component is encapsulation layer. As its name suggests, it encapsulates the stiffness control structure and caps the two ends of the actuators. It is made of stiffer silicone rubber, so it also acts as a strain-limiting layer. The last component is the stiffness control structure. Unlike the position-dependent stiffness of actuators, this structure can control the manipulator stiffness without position dependency. In our specific design, the structure consists of three independent revolute joints and embedded pressure chambers, one for each. Each joint can be pressurized up to 6 bar and positioned within 30 degrees bidirectionally. Together with modular and scalable design, the rotation angle and length of the structure can be modified for further needs. Each joint consists of two rigid links, a pressure chamber, and alignment pins. By the integration of two rigid links, a rigid compartment in revolute joint form appears, and the pressure chamber is positioned in it. Upon pressurization, the chamber expands and fills the gaps left between the rigid compartment. That causes the increasing of stress and final friction at the contact surface between the soft pressure chamber and rigid compartment walls, so that it becomes possible to increase the joint stiffness through input pressure. When the pressure is removed, the stress and resultant friction decrease, and the joint returns to its less stiff state. So we can say that stiffness of the joints can be controlled reversibly. Moreover, due to the pressure-based stiffening mechanism, transition time between low and high stiffness states is less than 1 second. Without pressure, our stiffness control structure is compliant and freely bends. Thanks to independently controlled joints, It's possible to obtain partial or total stiffness by pressurizing desired number of joints in various combinations. In addition, having independently controlled joints allow us to maintain various configurations. It can be straight or non-straight, like a zigzag. In this demonstration, we pressurize the joints at 6 bar. After following the pressurization, the structure returns to its compliant state. At that point, the first question may appear as how much the stiffness control structure affects the compliance of the manipulator. We measured the stiffness of manipulator with stiffness control structure and compared to manipulator without the structure. We repeated this comparison for different pressures at actuator up to 1.5 bar. Then we measured that adding the stiffness control structure reduces compliance of the manipulator by 30% on average. The second question is how much the stiffness control structure affects the end effector path and bending angle of the manipulator. We pressurized one actuator up to 1.5 bar and then depressurized it. We repeated this sequence 10 times and tracked the end effector path using a magnetic tracking system. And we calculated that adding the stiffness control structure into manipulator increases the precision of fallout path by end effector by more than 90% on average. On the other hand, adding this structure reduces the bending angle of the manipulator by 30%. The third question could be how the number of joints affects the obtained maximum stiffness. We tested structures with 1, 2, and 3 joints. After pressurization of the joints up to 6 bar, we measured the stiffness of each configuration. In our specific design, which includes 3 joints, the stiffness of the overall structure increases 5-fold at maximum input pressure. The final question is how much the stiffness control structure contributes to the overall stiffness at different manipulator positions. We tested 3 manipulator positions by pressurizing one actuator. First, no pressure, which is straight manipulator position. Second, 0.75 bar, and last 1.5 bar. At each position, we pressurized the joints up to 6 bar at the same time to obtain maximum stiffness contribution. Then we measured that the structure increases the manipulator stiffness up to 35%. In conclusion, we demonstrated a manipulator which has independent actuation and controllable stiffness with simple air pressure, while 2 fiber reinforced actuators control the position of the manipulator in plane. The stiffness control structure adjusts the stiffness of the manipulator without position dependency. The stiffness control structure has 3 individually controlled joints which allow to obtain partial stiffness. Thanks to the modular and scalable design, the number of joints can be increased or decreased. It's possible to use the proposed concept when a manipulator with different scale or bending amount is needed. With current configuration, we achieved up to 35% controllable stiffness increment. The proposed concept can be used in various applications which need improved safety but also controllable stiffness. In future works, we intend to miniaturize the manipulator. We aim to keep the diameter less than 15 mm to be used for surgical applications. In addition to demonstrated in-plane bending, we want to develop a manipulator by adding the third dimension using spherical joints while maintaining position-independent stiffening concept. And also, we want to add deformable and stretchable sensors into the actuators for position feedback. It will allow fixing the manipulator position against the disturbances in an unknown environment. This concludes my presentation. Thank you for your attention.